Welcome everyone. For today's prep, we're going to try a couple substitution rule problems. And the first one we're going to start with is example 3. So this is about where we left off in class the other day. We have the integral of 3x squared over x cubed plus 1. All right, so what are we going to do? Well, a helpful thing when we have a more complicated integral like this is to try and break the function apart to look at the pieces. And that's what we're going to start with. So we have a fraction, and sometimes a useful thing to do is to break that fraction apart. So we're going to take this 3x squared, we're going to peel it off, we're going to put it next to the dx there. So this is going to give us 1 over x cubed plus 1 times 3x squared dx. All right, so looking at this function now, there's kind of two pieces. We have this 1 over x cubed plus 1 piece, and then we have the 3x squared piece. And the function we have here is not one of our basic antiderivatives, so we know we're going to try maybe substitution rule. And we want to look for, out of these two pieces, we want to look for the more complicated piece, because that's usually where we get the idea for u from. So in this one, I would say this 1 over x cubed plus 1 is the more complicated piece, because it's a fraction, we're dividing by x's, it's more going on than just the 3x squared. All right, so our first step is going to be, we got to choose u. And then once we have u, we're going to calculate du. All right, so let's choose u, and then we'll calculate du. And we're going to do that from this complicated piece. And again, it's helpful, especially when we're getting the hang of these. Let's go back up. So how do we choose u? What's our strategy? Well, we're looking for that complicated piece, the more complicated piece of our function. And if we see a bunch of stuff inside parentheses and then all of that raised to the power n, we're going to let u equal the stuff inside the parentheses. If we see an exponential function with a bunch of stuff up in the exponent, well, we're probably going to let u equal the stuff in the exponent. Now, for the one we're looking at, we have a fraction. We have 1 over some things. So our idea here is we're going to let u equal all that stuff in the denominator. And the reason why we're going to do this is because that's going to convert it into a fraction 1 over u, and we know how to get the antiderivative of 1 over u. All right, so our idea here is to let u equal the stuff from that denominator. So let's try it out. All right, so u is equal to, and the stuff in our denominator here is that x cubed plus 1. So we're going to let u equal x cubed plus 1. All right. So that's part of the first step. The second part then is we gotta calculate du. So we got to calculate our differential. So the derivative of x cubed plus 1 is 3x squared, and then we multiply by dx. Okay. So once we have those, then we're ready to kind of substitute in our pieces. So we make our substitutions. So what are we going to do? Well, it just so happens, worked out very nicely, that the 3x squared times dx matches up perfectly with our du. So we're going to fill that in. And kind of by design, that x cubed plus 1 from our denominator, from that more complicated piece, well, we're going to fill that in. We're going to replace that with u. So we're going to make our substitutions. We're plugging everything in here. And so when we do that, our integral, instead of the 1 over x cubed plus 1, we're going to change that x cubed plus 1 to just a u. So we're going to have 1 over u. And instead of the 3x squared dx here, we're going to replace that with our new differential, du. So we replaced the u and the differential there. All right, so now we have a much easier integral to do. This is one of our basic antiderivatives. So now the next step is, well, figure out the antiderivative. So we're going to get that antiderivative. All right, so 1 over u integrates to just natural log of absolute value u. And we found the antiderivative, so let's put in our plus c. And then our final step, once we have the antiderivative, we just got to get it back to x. So the last step here is convert back to x. Plug back in the original variable. So we're going back to x, or whatever the original variable is. So in this case, it is x. So in place of that u, we're replacing this u here with the x cubed plus 1 from before. And there we go. We got our antiderivative. All right, so we kind of got lucky in this one. So when we took this 3x squared off and we moved it next to our differential, it matched up perfectly with what we calculated for du. And so far, the examples we've seen, we've always kind of gotten lucky like this, where everything matches up perfectly. So we're going to try example 4 in class. This idea of getting the differentials to match. So in this example, the du we calculated was the 3x squared dx, and that matched up perfectly with those leftover terms that were in our integral. And this doesn't always have to happen. And in fact, usually it doesn't happen. So we're going to try one more example just to see how this might look. All right, so let's try example 5. So we're going to find the antiderivative of the square root of 4x plus 5. And usual things for antiderivatives and derivatives, we want to rewrite that square root as a power function. So let's rewrite this as 4x plus 5 raised to the 1/2 power. Okay. So again, the first step is we got to figure out what our u is and du. So we got to calculate those things. And we see this nice set of parentheses here. We got a bunch of stuff inside of it, and it's being raised to a power. So we're going to let u equal the stuff inside those parentheses. So u is equal to 4x plus 5. All right, so now we want to calculate du. And the derivative of 4x plus 5, what is it? It's just 4. And then we multiply that by dx. Okay. So far, so good. Now the next step is we got to substitute these pieces in. Now let's look at our integral. The 4x plus 5, that's going to become u. So that'll be taken care of. But now if we look, in the differential we calculated, we have 4 times dx, but in the original integral, we only have dx. So you want to just kind of compare here. So the only things that match up are those dx terms. And we have this extra constant, this 4, in the differential we calculated. So this is going to pose, a slight issue for us. So what are we going to do? Well, the idea is we're going to solve this differential for dx. Solve for the matching terms. So the dx is what matched up. So let's solve for that dx. And when we're working with these differentials, just think of them as like a variable. It's just a fancy name for a variable. It's normally our variables have just a one-letter name. These variables have a two-letter name. So we're just going to solve this equation for the dx. And to do that, we're going to divide both sides by 4. So when we do that, we end up with dx is equal to 1 over 4 times du. So again, we just divided both sides of this equation by 4, and I'm just writing it as 1 over 4 in front there. All right, so now we're ready to go. Now we're ready to substitute in. So we're going to be able to fill in our u term there. Nice and easy with that. And then that dx that we just solved for, well, we know what dx is actually equal to. So we're going to be able to fill in that. So now we make our substitution. Yeah, we'll leave it there. All right, so that 4x plus 5 is going to become u. So it'll be u raised to the 1/2. And then that dx is going to be 1 over 4 times du. So again, the u term there we've plugged in, and that dx, our differential, became 1 over 4 times du. All right, so now this is a basic antiderivative. We have a power function and then just a constant multiple. So now we're ready to do the integration, and that's step 3. So we're going to do our antiderivative. So what is this? Well, the 1 over 4 is a constant multiple. So let's just take that 1 over 4 and we'll just kind of move it out in front. And then we can focus on getting the antiderivative of that u to the 1/2. So the variable is u. We add 1 to the exponent, so that takes us up to 3 over 2. And then we take that new exponent, flip it, put it in front of the u term. And we're doing an indefinite integral, so plus c at the end. And now we're just about done. We got our antiderivative. Last step is we just convert it back to x. So we're going to convert back to x. And while we're at it, maybe simplify. So the 1 over 4 times 2/3. The 2 cancels out one of the 2's inside the 4 there, so we end up with a 1 over 6. And then in place of that u, we're plugging back in our 4x plus 5. So we have 4x plus 5 raised to the 3/2 power, and then plus c. So we just went back. And there we go. We got our antiderivative. So this example is showing us that sometimes the differentials don't match up perfectly, and we have to do a little bit extra work in order to kind of get all the pieces to work nicely. So we're going to try some more examples like this. So we'll see you then. Bye-bye.